in this part of the tutorial, we will focus on learning. And learning here refers to two different things that are yet closely related. One is the idea of given data, how can we learn a manifold that has like a complete geometric structure? And secondly, given a manifold and data distributed on it, how can we do basic statistics? And that's sort of how this part of the tutorial will be given as well. It'll be like a part 1 and a part 2. And I'm in the lucky situation that this is not the opening act of the tutorial. So by now, I can trust that you're all renowned experts in differential geometry. Don't worry, we will only have to use like the most elementary parts of differential geometry, which I'm summarizing here on this slide, which is basically that given a Riemannian manifold, we can define geodesics, shortest paths, as curves that minimize the length between 2 points, where the length is simply measured according to the Riemannian metric of the space. When we actually compute these geodesics, we don't do it by minimizing this length, but instead we minimize the energy, which is this quantity here, if you can see my mouse. And it's the exact same thing, except there's a square root missing, so it's much more well behaved. We will also be using things such as exponential and logarithm maps, so operators that map between manifolds and tangent spaces. And finally, the beauty of all of this is that everything I've listed above are direct artifacts of having a metric, a Riemannian metric, so smoothly changing locally defined inner product. Once you have that, once you have the Riemannian metric, you can derive the exponential maps. You can derive expressions for the length of a curve and thereby arrive at a notion of a shortest path and so forth. So from a practical perspective, once you have a metric, you have everything. Okay, this is basically all I need you to know about differential geometry. And I'm hoping that you will have seen the bulk of this previously today. And on that, let's just jump into the first part, where we will start estimating manifolds from data. So for the purpose of simplicity, we'll sort of assume that we are given data that's distributed in a real vector space. And now we want to find a low-dimensional manifold that has a Riemannian structure that should sort of roughly follow the trend of the data. And I'm being fairly loose in my definition here because we will explore different ways of doing this. And consequently, we will need sort of different ways of formalizing things. Okay, so my sort of favorite thing out here when it comes to learning manifolds is this 20-year-old work by Guy Lebanon. And I think he was sort of the first to like link the density of data to Riemannian metrics. And I think he did this in a very elegant way. And I'll start by walking you through this. So assume that you have some density estimate. We'll just call it P of X. And it doesn't really matter how we got it. It's just something. It could be a Gaussian mixture. It could be a kernel density estimate. It could be a variational autoencoder. It could be a diffusion model that allows you to evaluate densities or whatnot. Doesn't really matter how we get it. So then this idea that Guy Lebanon put out there was, can we define a metric, G, such that geodesics, shortest paths, are attracted to high density regions? And since we kind of know that when the density is high, we want the metric to take small values that would have the property of attracting, letting shortest paths be attracted to high density regions. So we simply say, we summarize the metric, or rather we say that the determinant of the metric, so the volume, should be inversely proportional to the density. And if we then go ahead and say, well, since the density only provides us with a scalar constraint on the metric, then let's just assume that the metric is a scalar times the identity matrix. And that scalar here is given by lambda. So with that, you can sort of shuffle things around, and you quite easily see that you must then have that this lambda, this scaling of the metric, should simply be inversely proportional raised to a power of the dimension of your space to your density. Then the equations above are satisfied. This is a really, really simple thing. Once you have a density, you can directly arrive at a metric. And here I'm showing you sort of a simple data set alongside a density estimate. And if I then start computing geodesics under this metric that was proposed before, you'll see curves like this. And you quite clearly see that they follow the trend of the data. They're attracted to high density regions, and it's all very nice. You can sort of easily imagine how you can leverage this type of structure to build more elaborate algorithms. And that's great, done. Basically, at this point, you can say manifold learning is now solved. And you will play, by the way, you will be playing with this particular problem if you do the collab later on. Okay, so what's great about this is that it's easy to understand and actually works. You get the type of behavior that I just shown you in the plot if you implement this, and you really only need access to an unnormalized density. So even energy-based models or whatnot can be used here. Now, the only issue, and it's a rather significant one, is that it scales poorly with dimensionality. Simply computing geodesics and whatnot in high dimensions quickly gets frustrating. So even if you have a great density estimate for high dimensional data, this will not be a great approach because of the computational costs associated with computing everything. So a natural next step is to then say, can we find some sort of intrinsic low dimensional structure that captures the essence of the data, and then restrict our manifold to only look at these. And that's what we'll do next. And we'll do this in the form of latent variable models. So here, I'll mainly be talking about variational autoencoders, but the bulk of what I say will be generally applicable to latent variable models. So these are structured such that you assume that your density can sort of be recovered through a set of latent variables, here denoted set. And we then integrate them out to produce the density, P of x. The most prominent example these days is the variational autoencoder, which is by now like an established approach that says, okay, assume that these latent variables follow a Gaussian distribution, just standard Gaussian. It's an arbitrary choice, but it's one that we have to make some choice. So we make this particular arbitrary choice. And then in the case of a so-called Gaussian VAE, you assume that the mapping from this latent space out into the observation space is sort of determined by a Gaussian. And we can equivalently write this as we assume that the data is generated by mapping. Let's see, if you see my mouse, then you can sort of map from latent space through some neural network mu, and then add Gaussian noise to that. So visually, you can think of a variational autoencoder as something that has a low-dimensional structure, a low-dimensional Euclidean structure. This is then mapped out into a high-dimensional space through a neural network, and noise is added. Now, what I want to do here is I want to use this low-dimensional structure to make computations more feasible. So let's sort of focus on the latent space here. If I zoom in, then here I've highlighted 3 points because I want to make sure that we sort of understand this latent structure. So here I've highlighted 3 points, and they correspond to 3 images. In this case, this is estimated from MNIST. And what you quite quickly see is that the 2 zeros I've highlighted are quite far away from each other, whereas one of the zeros and a 1 are rather close to each other, which could sort of lead to the conclusion that 0 and 1 are more similar to each other than 0 and 0. And this is obviously like an incorrect conclusion. So let's dig a little bit into this. So the model, again, is you have a bunch of Gaussian distributed points in the latent space, and you have a mapping out into observation space. And let's just, for the sake of argument, assume that we fitted this model optimally. There's a whole literature on how to do approximate maximum likelihood in this model, and it's fairly reliable. So you can actually fit these models easily to data. But let's assume that we have a fit. Then what I'm going to do is I'm going to construct an equally good model, and it's going to be equally good because it's going to be identical, but it's going to have sort of a different structure, and that's what will make things complicated. So what I'm going to do is I'm going to deform all my latent space by some nonlinear invertible map, and then I will rephrase the original mapping from latent space to observation space. I'll rephrase that as first just inverting this deformation of the latent space and then applying the previous mapping. So basically all I'm doing is I'm introducing a deformation and then I'm undoing it. But the issue here is that I'm doing it in a way where I'm not changing the latent distribution of my data, and I'm not really changing the reconstructions of my data either. So I'm not changing anything in the model, except I'm changing the latent variables alongside with the map that takes you from latent variables to observations. So really, I haven't changed the model, but the latent space changes a lot of structure. And this is rather problematic because it prevents us from doing any sort of meaningful calculations in the latent space, because we never know, are we observing just an arbitrary deformation of the latent space? So in terms of statistics, we say that the latent variables are not identifiable. But in practice, what this means is that we should expect to see arbitrary instantiations of our latent variables when we fit them to data. So to give you sort of a practical example of this is the specifics of the data here are unimportant, but this is real world, highly complex data that we fitted where we fitted a latent variable model that just has a 2-dimensional latent space. And I'm just running the same code 4 times. And the only thing I'm changing is the random seed used to initialize my model fit. And what you see is that you get somewhat similar looking latent representations across seeds, but there's a lot of local differences in how things are structured. You know, sometimes you see these branches sticking out, and which branch is a neighborhood to which is close to which differs from plot to plot. So it means it's rather difficult to do any form of analysis on these latent spaces. Okay, so the good news is that you're at a geometry tutorial, and this is exactly the classic problem that was solved by differential geometry. So the solution, the way you make the latent space more well-defined, is that we're going to endow it with a geometric structure. And the construction goes as follows. So assume that you have some curve in the latent space. And now you want to determine the length of that curve. And the way we're going to define that is that we'll simply take this curve, map it out into observation space, and measure the length of the curve out there. That is not influenced by however the latent space is deformed, because the actual measurements are performed out in observation space. And this, you can sort of apply the chain rule to the length expression I have on the slide, and then you arrive at that this induces a Riemannian metric over the latent space, which is just the Jacobian of the mapping F multiplied by itself. This is known as a pullback metric. And what's beautiful about this particular metric is that it gives you computations that are invariant to reparameterizations, meaning that all these different deformations you might encounter of your latent space, they disappear once you start working under this Riemannian metric. Okay, I'm getting about a bunch of
온수 나와야 되는데 안 나와?
몰라. 아직 뜨겁긴 안 해봤어.
온수 해놨는데
그래? 온수 나오는 게 맞아.
목록으로 돼 있는데.
여기서 했다.
right now, but I'll continue anyway. Okay, so if you think about this, this is rather exciting because what it means is that just by fitting something as simple as the variational autoencoder to data, you've now actually learned an entire Riemannian manifold with its complete structure available because we have a simple closed form expression of its metric. And that's really cool because now we can leverage that geometric knowledge to actually build stuff. And I just want to test that out. Just verify with a simple toy example that this geometry, really understands the essence of my data. So what I've done is that I've created a simple one-dimensional circle lying in a two-dimensional space. And then I embed it in a 1,000-dimensional space and start bending it and twisting it a little bit, just a little bit. I don't want to make it too difficult, but it also shouldn't be a completely linear thing. So we kind of know that the true underlying data manifold here is a circle. And then we would expect that shortest paths, geodesics, would sort of roughly follow this circular structure. So I'm going to fit a variational autoencoder to that. And I've done that here. And I get this wonderfully circular latent representation. Clearly, the underlying pattern has been found. And now I want to compute geodesics, shortest paths, on this manifold given by the variational autoencoder. And yes, I've said that. And basically, whenever I show you this type of plots, I'm also going to show you the determinant of the metric as the background color. This should give you an indication of what happens in the space. Anyway, now I'll show you the actual shortest paths you get by computing geodesics on this manifold. And what they are is that they are paths that just cut across the hole in the circle. So clearly they are not capturing the circular structure of the data. So these geodesics may have nice mathematical properties, but they are not reflecting what's actually happening in my data. So I've sort of constructed a beautiful mathematical theory that's completely useless. It has no resembling to my data. And that's kind of unfortunate. But if you think a little bit about it, this is not surprising at all, because what the variational autoencoder does is that it sort of tries to take a Euclidean plane and deform it such that it interpolates your data. And what that means is that it will sort of try to smoothly interpolate across whatever holes you might have in your data manifold. And since we regularize these models quite a bit, they actually are quite smooth, even across holes. And that means that shortest paths will naturally be attracted to these very smooth regions. So shortest paths will naturally cut across holes rather than walk around them. Too bad. Okay, but actually what I did here was that I looked at the mean function of the variational autoencoder. And previously I had defined as the variational autoencoder as being this mean function plus some Gaussian noise. And I was disregarding the noise for it. Let's see if we can somehow put this noise process into play. Perhaps there's something meaningful to be had there. So the only issue with that is that now we have some sort of notion of a stochastic manifold, and all the beautiful differential geometry we have available doesn't apply to stochastic objects. It only applies to deterministic objects. So we somehow need to take our stochastic object and turn it into a deterministic one if we want to apply differential geometry. So let me just take a sip of water. So the way we'll do this is that we'll note that if you look at the equation that I have for how to define x, which is x equals mu of z plus e times sigma of z, I can rewrite that equation simply by stacking mu and sigma, these two neural networks that map from latent space to observation space. I can stack them on top of each other to basically form a map from the latent space into a space that's 2 times as big as my observation space. And then I can form a random projection, which is recovered by this identity put together with the Gaussian matrix E. And I can sort of form a random projection of that. So what that means is that you can think of the variational autoencoder as being something that decodes, that maps into a space that's given by a mean and a standard deviation, and observations are then generated by a random projection from that space into the observation space. Now, what we can then do is we can look at the geometry of this map into the space of the mean and standard deviation. And if we do that, we get like a volume that looks like this, and geodesics that start to actually follow the circular trend of the data. So all of a sudden, we went from something that basically disregarded the structure of our data into something that really captures the essence of what's going on. So how on earth did that happen? Okay, let's first look at the model that only considers the mean. In this particular case, the length of the curve, you arrive at that by sort of integrating the Jacobian of the mean by the velocity of the curve. That's sort of just straightforward following the chain rule from the definition of the length of a curve. If we do the same thing in the stochastic setting, then we see that we have to think about this concatenation of the mean and the standard deviation. That then splits out into a Jacobian for the mean and a Jacobian for the standard deviation. So somehow this additional Jacobian is the difference that all of a sudden makes geodesics become attracted to data. And the way you should think of this is that the standard deviation in a well-estimated sort of maximum likelihood estimate of the model, that standard deviation will grow once you move away from data. So that means once you move away from data, the Jacobian of that standard deviation starts obtaining large values, and that will then penalize short paths. So somehow the uncertainty, the standard deviation, is building a wall around the data, because that's where uncertainty starts to grow. So you can sort of think of stochasticity as being like a topological hint. Gives you an indication of what's the actual topology of your data manifold. And I think that's kind of neat. This idea that when we don't know what's happening, what our model is supposed to do, then that's a hint that we're off the manifold, so to speak. Okay, so let me show you an example from robotics, given that this is a robotics meeting. So this is an example that that Lionel has been doing with one of his students, Hadi, and I've had the pleasure of helping a little bit. In this particular case, we are given trajectories of how the robot should be moving, and then we fit a variational autoencoder to these trajectories, just completely ignoring the temporal dimension. And what you see on the left are the latent representations of this data. And what we then simply do is that we compute geodesics. And so basically, we now sort of say, give me the geodesic from the initial position to the position where the first cup is. Then you move along that geodesic. That's sort of what the robot is doing. It's just moving along geodesics. And I think that's kind of cool. What's neat about this example is that the robot was trained on, where it's shown how to go from an initial position to each individual cup, but not how to go between the cups. And with this representation, you can just have geodesics that sort of go between cups, and thereby you can sort of complete the set of motions available. I think that's kind of fun. This is sort of another example of the same thing, just where the latent space is three-dimensional. Here we're sort of trying to visualize the metric in yellow. So the contours you're seeing are regions where the metric obtains small values. This is basically where it's cheap for geodesics to walk. It's mostly just an excuse to show off this fancy plot that Hardy made. Okay, but what's really cool about this approach is that what we're basically doing is that we are assuming that we have a Euclidean metric in the observation space, and we're bringing this metric into the latent space. But we can replace this metric with any other metric that we care about. So we can place another metric in the observation space, in the ambient space. And what we're doing here is that we're just modifying this metric a little bit, such that if there's an obstacle, we let the ambient space metric take on very, very large values. And that has the effect that it becomes very expensive for a geodesic to walk near an obstacle. So now you can sort of take a pre-trained variational autoencoder and you can start playing with the metric of the observation space at runtime, because you can sort of move that around without changing the VAE. And through that, you can then get obstacle avoidance directly into your geometry. I think that's kind of neat. Okay, so that's sort of the first part of what I want to talk about today. So the second part is, given that we have a manifold, it could be a manifold that we've learned from data, but it could also be a pre-specified manifold like the rotation group or the quaternions or whatnot. Given that we have data on those, how can we do at least basic learning? Due to the interest of time, we won't dive into highly complex models, but rather try to sort of scratch the surface of what are the statistical problems you face once you start getting into learning on manifolds. So in general, there's this entire field called geometric statistics, which is concerned with how to do statistics on mostly manifolds. And it is not as well developed a field as the Euclidean statistics that we're used to dealing with. And that's not because the people working in this field are not smart, it's simply because it's a lot harder. You face a lot of low practical issues once you start doing statistics on manifolds. So the general strategy that people follow in this field is that they say, okay, I have some statistical quantity of interest, and I want to generalize that from the Euclidean domain to the Riemannian domain. And this is then done by picking a property of that statistical quantity and then generalizing that property. The issue is that many statistical quantities have many properties, and depending on which one of those you pick, you end up with different Riemannian generalizations. So we're going to do an example of that. So let's look at the average of a set of points that are on a manifold. And then we will sort of try to sort of derive a notion of an average on manifolds. So We'll sort of start with the most common version, the one that people actually use, which starts off with the idea of defining the variance of a set of points, but with respect to a base point. That base point is called mu here. So all this equation says is that we define the variance of a set of points with respect to a base point mu, find that as the average squared distance from my data to the base point. So this is exactly the same definition of a variance you would have in Euclidean spaces. And if we sort of take the case of a learned manifold, then if the purple point is our base point, then we can compute shortest paths to that base point, measure the length of these shortest paths, and then square those lengths and add up the numbers. That would give us a variance of this data set with respect to the base point mu. If you pick a different base point, you get a different number. Okay, so what's then known as the Frechet mean of a given data set is then the point that minimizes this variance. This is exactly how you can this is a property of the Euclidean mean, that the mean is the point that minimizes the sum of squared distances to your data. Some people define the mean this way in Euclidean spaces, and you can sort of take that definition directly applied. The only issue here is that because the mean is now defined as a minimization of something, that also means that we cannot trust the result to be unique. So if you have a data set and you ask what's the mean of your data, according to this definition, the result may not be unique. There may be 3 means of your data, or there may be infinitely many means. So for example, if you have uniformly distributed data on a sphere, then the entire sphere is the mean. So it's we have to wrap our head around the idea that means are not necessary, that you may have more mean values than you have data points. And that's rather like funky, I think is the best word I can come up with. But so be it. That's a complication of working on manifolds. So as you can sort of guess, the way you would actually compute this in practice is that you would write up your variance function, and then you would compute a gradient of that and just minimize. And that would give you a local minima of this variance function. These local minima are often called Karcher means, because Karcher and Grove studied this stuff back in the 70s. But if you ask Karcher himself, then he will wildly object to the terminology of calling it a Karcher mean. He thinks it's deeply problematic, and he has even written papers about how problematic he thinks that name is. It is nonetheless the most commonly used name out there for local minimizers of the variance. So what's really nice about the Frechet mean, or these local minimizers of the variance, is that they're quite easy to arrive at algorithmically. So if you have data that's on a manifold, the way you actually compute the Karcher mean is that you pick a random point of initialization. Usually this is just a randomly chosen data point. Then you take all of your data, you map it to the tangent space of the mean. So that's just applying the logarithm map. So now you have your data expressed in the tangent space of your current estimate of the data. Your current estimate of the mean. In that tangent space, you can now go ahead and compute the average of your tangent vectors. So the tangent space is Euclidean. So you just compute the Euclidean average of your tangent vectors. And then you take that point in the tangent space and map it back to the manifold. Now, that gives you like a new point on the manifold, which you can then use to repeat the procedure over again. So now you repeat the procedure, you map the data to the tangent space at this new point, take the average in the tangent space, map back to the manifold, and so forth. And this thing here is a Newton-style optimizer of the variance function. So it's a quite efficient optimizer. And as you can sort of imagine, it's dirt easy to implement. It's just a few lines of code once you have access to logarithm and exponential maps. If you don't have access to those, it's a little bit more tedious. But in general, it's a very simple and very intuitive algorithm. Okay, so we have means, we have variances. So we kind of also want covariances. That would be nice. And people tend to define them in the exact same way, which is that you have a base point, mu, and then you ask, what is the covariance of your data with respect to that base point? And the way you define this covariance is that you map your data to the tangent space and compute the second moment of your data in the tangent space of your base point. And usually people pick a Karcher mean as that base point. Now, once you have that covariance, you can start doing the usual things we do with covariances, such as eigen decompositions. So if you find the leading eigenvector of that covariance, that's now sort of a direction and tangent space that spans a geodesic. This geodesic is known as the principal geodesic of your data. And it's sort of used as a substitute of PCA. And it's to be fair, it's a rather crude approximation because it relies on linearizing the manifold. So it only really works well if your data is concentrated around your base point. If it's not, it tends to give you highly distorted statistics. The thing is, this is often all we have. So we have to settle for this type of approximations. Okay, one of the things that really bother me in what I've shown you so far is that the Frechet mean, the Frechet variance, the covariance, whatnot, these are not maximum likelihood estimators under any known model. So usually I would go on about defining statistics in Euclidean spaces by assuming a probabilistic model, such as my data is Gaussian distributed, and then I would derive maximum likelihood estimators of the key statistical quantities of interest. This I have not done here. I've just taken some properties of the mean and sort of pushed that over to the geometric setting. And it makes it a little bit unclear what we're actually doing. And yeah, that's a little bit problematic in my mind. Well, on the slide, it's deeply problematic, but I do find it rather problematic. So why are we not then not just doing maximum likelihood? Well, the reason we are not doing maximum likelihood in general when we learn on manifolds is that we rarely have distributions to work with in the first place. So we kind of take it for granted when doing Euclidean statistics that we know normalization constants of various distributions. So for instance, if you work with the normal distribution, you readily use that the normalization constant of that normal distribution is known in closed form. On manifolds, this is very, very rarely the case. We almost always never have access to normalization constants of distributions. So this is a big issue, and all of this is because integration is more difficult on manifolds. Okay, so one procedure that people take is that they wrap distributions onto manifolds. So I put on this picture of a ball that's being put in gift wrap, because that sort of kind of shows what's going on. So you imagine that you place a distribution in the tangent space of your manifold You choose some tangent space, you place a distribution there, and then you map it down to the manifold. And with this, you have to take into account that the tangent space extends to infinity, but your manifold may be compact. So you can sort of wrap around multiple times around the manifold. So you have to take that property into account, and you have to take the distortion that's induced by the map from the tangent space onto the manifold into account as well. And you can do this, like at least the second part, the distortion we can sort of work with. And with this, like, I'm not going to take you through the equations of doing that, but it's just a matter of tracking Jacobians of exponential maps. And with this, you can sort of just define some distributions. The only issue with that is that it's kind of hard to build intuitions about how these distributions behave, because we may have intuitions about how they behave in the tangent space, but the tangent space gives you a highly distorted view of the actual manifold. So whatever properties you may like tangentially, they may behave very oddly on manifolds. And this is a thing. However, you can still use this quite efficiently, because you can use this as base distributions in normalizing flow style models. You can use it to define wrapped Gaussian processes, and they tend to only look so locally that the wrapping doesn't introduce much distortion and whatnot. So this is a useful tool for going forward. In the interest of time, I won't go more into it. Instead, I'll sort of wrap up, and I'll sort of say that what we've seen is that we can estimate metrics from data. But once we go to higher dimensional data, we tend to need to plug in some form of dimensionality reduction in there to make it feasible. And sorry. Okay, and when it comes to actually learning on manifolds, then I think it's fair to say that it's still a highly moving field. We haven't really settled how to work with statistics on manifolds in an efficient way, but we have some basic tools that are, if nothing else, useful. They're not perfectly understood mathematically, but they do remain useful. The local means are actually valuable for actual computations. Okay, there are some references here. I won't go into that. So what will happen next is that we will do a practical session, but perhaps we should do questions first in case there are any. So do jump in if you have questions. Otherwise, I'll switch to showing you some practicalities.
Okay, thank you, Søren, for the talk. Can you hear me? We are testing sound again.
Yes, yes.
Oh, wow, beautiful. Thank you so much. Okay, then I will leave the floor for questions. Thank you for the talk.
You're welcome.
Thank you. Thank you very much, Søren, for the very nice presentation. I have a comment considering the tutorial nature of the things and a question. The comment is, because I hammered a lot when my previous talk saying that you cannot take determinant of matrices and you cannot write J transpose times J. So I would like to explain why you did, because you can do that, but you intrinsically actually consider that your data are embedded in a Euclidean space. So between J transpose and J's, there is an identity which is the Euclidean space of your embedding, and you do exactly the same in the other point, to make it clear for those who follow my talk before. Now a question. You, in the last things you said about the wrapping, of course, the wrapping is a problem of topology, right? So it's really the topological nature of the manifold you want to embed. Do you think, because I would say, you know, considering that is clearly a topological problem, you should use cohomologies in order to study that. Have you thought about that?
I don't think I'm smart enough to answer that question. I have not thought about it. I think you bring on a very, very key point by saying that a big issue with topology is that, a big issue with wrapping is that you start off by looking tangentially at things. plug on some Euclidean structure, some Euclidean distribution on that, and then it's like, well, let's just squish it down to a manifold, disregarding however that manifold may look. And I do think you're very, very right that topology is a big issue. So if, for example, if you do this on the sphere, you have to deal with this infinite wrapping. And that's a problem. If you do it on other manifolds, you don't. If there's a hole in your manifold, that's not going to be evident in your tangent space. And what then happens?
That's right, and this really has to do with the Riemann cohomology. So if you want to talk about it, we can, because I think there is a way to do that, but it's a topological problem. You agree with that, right?
Very much, very much.
Yep. Thank you very much. Very nice talk.
Okay, thank you, and I would love to talk more about this stuff. So as to your comment, you're sort of very much right that what's happening in these metrics, these pullback metrics, is that we're assuming that we have a Euclidean metric in the ambient space, and without this ambient space has higher dimensionality than the latent space.
Yes.
So when you assume a Euclidean metric, you sort of squeeze in an identity between the two Jacobians. And in principle, you can assume any like Riemannian metric over the ambient space, and then that would just appear in between.
Precisely.
And the reason why all of this works is because the latent space is lower dimensional than the ambient space. And that means this metric G has low dimension times low dimension. And that means, like, under very, very mild assumptions, this is a full rank matrix.
But it's the only thing I'm saying is that you do consider Euclidean structure in the data. Otherwise, you couldn't do that. That was my comment. And also, for example, when you take the determinant of G, actually what you do is the determinant of the Euclidean metric inversed times G, because then becomes a linear operator if you take the identity of the data in G and you take the eigenvalues, basically the determinant. So you need, so basically what you do, you assume in what you do a Euclidean structure on your data. That's it. Or another structure, as you rightfully said, that would appear there, right?
Yes, exactly. And I think this is absolutely essential because basically this forces you to think about what if my data doesn't have a meaningful Euclidean structure? In that case, you should not do as what I'm proposing. You should really be thinking differently. The general mechanism of looking at pullbacks and whatnot, of course, that extends to arbitrary manifolds. So if you have data that lies on a sphere, of course, you can learn like a low dimensional submanifold of that sphere and then use a pullback metric to describe that, but it gets a little bit more involved.
But you cannot, I think it's an interesting issue, right? Because data, if you don't have distance of data in the first place, basically that's what I'm saying. You cannot say anything anyhow, because you can stretch them all around. So you need a structure on the distance of your data you start off with. That's the point, right?
And I think, to me, philosophically, I think that's a fair thing to assume. Like, I would never dare to do any form of statistical analysis of data where I had no idea how to even compare pairs of data observations. Like, if I really had no structure whatsoever on the data, then I would not dare to do statistics. But I think it's an interesting debate, this notion of how little structure can you get away with assuming on your data. And I don't feel like I have an answer to that like line of thought. But at least currently, I feel more comfortable doing statistics on data where I have some notion of distance that I can at least trust locally.
That's all you need. I think that the minimum structure is distance. Thank you very much. Very nice talk. Thank you.
Thank you, Søren. Anybody has another question? We have time, I think, for one. Take that one. We know that it works.
Yeah, thank you so much for the talk. You mentioned about this warping a distribution on the tangent space to the manifold. My question is, are there any typical, easy to work with distribution directly defined on the manifold so that we can directly work with? If you can maybe introduce some of those.
I think, right. So I think the short answer beyond the uniform distribution, when that's defined, is no. we don't have easy to work with distributions in general. I think the closest we have to those would be diffusion or Brownian motion distributions. So if you sort of look at a random walk, you start somewhere, think of it as you start from your mean, and then you make infinitesimal random walks. And then that will sort of trace out random paths, and you can ask, well, where do I end up? What's the distribution associated with that? This is either known as sort of Brownian motion or diffusion. And a lot of properties are known about these distributions. We don't have expressions for their density, but we know how to sample from them. We have like a lot of information about the density, but we just don't have an explicit expression for it. So we can do a lot of things with these diffusion style models on manifolds, and the tools to do this are like rapidly expanding at the moment because of diffusion models being studied so extensively in machine learning. So all this score matching that people use to estimate diffusion models in machine learning, that extends to manifolds, and you can actually use that to learn surrogates of these densities of the diffusion. And I think that's the closest we have, but I wouldn't exactly call it like here's a ready to go distribution that you can just pick up. I think this is the big issue that we face in geometric statistics, is that we just don't have these distributions that are universally easily approachable.
Good to know. Thank you.
Thank you.
Okay. Thank you, Søren. So we can move to the practical session. What I will do is that I will leave the mic here, and anybody that has any question, you just walk here and you can directly ask to Søren. Søren, you have the camera watching us, so you should be able to also see the person asking question, correct?
At least I see a big room of people.
It's a big room of people, and you should see me standing somewhere.
Okay, it's all very, yeah, there you are,
Yeah.
you're standing.
Great. So the person asking question is going to be here and will just basically interrupt you. Is that fine?
It's fine for me, though. The original plan here was that I would have given you a Jupyter notebook on Google Colab that you could play with, where you would sort of do some of these computations yourself. And there would be some missing parts of the code that you had to implement, but I understand that there are like difficulties doing this in practice. So what I'll do instead is I'll sort of walk you through this Colab, and the first thing we'll do is that we will look at density metrics. That's this first thing I showed you, where you just take the density of your data and then you turn that into a metric. And I've sort of defined a class that will do this in a simple instance. All it does is that it computes like a kernel density estimate of data. So that just means for each data point, you place a Gaussian distribution around that data point, then you sum over that. So it's a giant Gaussian mixture model. Once you have that, then you can define the energy of a curve. So this will be the general structure. It's by far the most reliable way to compute geodesics, is that you define the energy of a curve. I don't know if you recall, we had that up here on the recap slide. It's this expression of the energy. And so given a curve, which in this particular case is just a discrete set of points, so we can do finite differencing to estimate the velocities. So all we do here is that we evaluate the density, we invert it, and use that to define a metric. And then I use finite differences to compute the curve velocities and use that to define the energy. So now you can sort of imagine that you can now differentiate through this energy expression, and thereby you can arrive at geodesics. And to sort of make something really simple for this tutorial, I chose to parameterize curves simply as second-order polynomials. This is a really, really crude assumption, but it makes the code very simple to follow. So what we'll be doing is that we'll be finding second-order polynomials that sort of have minimal energy and use those as proxies for geodesics. And then the actual geodesic computation is really, really easy. It just says evaluate the energy of a given curve, differentiate through it, and run your optimizer, whichever optimizer you favor. That's it. So you can see that just this notion of computing geodesics numerically doesn't have to be difficult in terms of code writing. And really, it's a variant of this code that we use to, actually do real-world computations. And then just to make it specific in the actual code, we download some data from my website and fit this density metric to it and just compute a collection of random curves exactly, or random geodesics in exactly this way. And then you get a plot like this. You sort of see that this is remarkably simple. And you could very easily just plug in some other density estimator to make this work in practice. So right up here in my density metric, I had a kernel density estimator. If you have some density estimator that's based on a complex neural network, you just plug that in here and it should just work. And in my experience, as I said in the presentation, as long as the space is reasonably low dimensional, this actually just works. So it's kind of neat. Okay, and now we can do the exact same thing, but with a variational autoencoder. So I'm sort of doing more or less what I showed you in the talk. And the bulk of this code is about defining the variational autoencoder. It's just you define a prior, you define an encoder distribution, you define a decoder. The variational autoencoder itself is then a combination of these three objects. And the interesting part is that we just want to compute the energy of curves. And this is remarkably simple. You just take a curve in latent space, you decode it, you measure the Euclidean energy of that curve, which is really just squared distances between points after decoding. And once you have that, you can run the exact same optimizer to find geodesics as before. So literally the code is the same. All we're doing is that we're changing the definition of what is the energy. Okay, here's just a training loop for actually fitting the VAE. And we're doing this on like on a subset of MNIST. And I'll sort of scoop over these details. You can play with the Colab. You can find the Colab on the tutorial website. So you can play with this yourself at home. But what you can sort of see is you can sort of arrive at exact, like similar style plots as before, where you have latent representations and random geodesics sort of roughly follow the structure of data. So the key point I want you to take away from this is that computing geodesics, like it's not difficult to code up. You look at these equations on screen and it's actually remarkably simple. All you have to do is that you have to be able to evaluate the energy of a curve. And then you just have to be able to differentiate that with respect to the curve parameters. That's it. Everything else is just off the shelf style code. What I'm showing you here is fairly unoptimized code. We have more elaborate code in the Stockman library from my group, where we do tricks such as batching of geodesics, such that you can compute multiple geodesics in parallel and whatnot. And that's pretty much it. So if you look at the past 5 years of work from my group, that's basically these few lines of code. So it doesn't have to be that hard. I think that's the main point. Any questions for this? Otherwise, I would recommend that you, whenever you sort of are in a situation where you can play with this stuff, is that you spend 10 minutes on just fiddling a bit with the code and see where that takes you. It's the main takeaway is that this isn't all that hard.